Modulation and demodulation of RF signals by baseband processing. Cruz-Emeric, Jorge Antonio. Abstract of dissertation presented to the Graduate Council of the University of Florida in partial fulfillment of the requirements for the degree of Doctor of Philosophy. Modulation and demodulation of RF signals by baseband processing by Jorge A. Cruz-Emeric, August 1976. Chairman, Leon W. Couch, Ph.D., Major Department, Electrical Engineering. A technique for modulating a carrier by a variety of modulation laws is analyzed. The technique is based on the separate generation of the complex envelope function by a baseband preprocessor. The complex envelope is then used to modulate the carrier. Since the complex envelope function depends exclusively on the modulation law and on the message signal, the baseband preprocessor can be programmed to obtain the desired modulation law. Direct generation of complex valued signals is not physically possible, so various alternatives exist to realize the modulation process, but it was found that only 3 are of practical interest. All systems considered were a combination of 2 modulators and 2 baseband preprocessors. The modulator combinations were an amplitude modulator with a phase modulator, a pair of balanced modulators, and a pair of phased modulators. These configurations were based on the possible representations of a complex function in terms of real-world components. Equations were obtained for the complex envelope components and their corresponding autocorrelation functions. The bandwidth required by these components were analyzed to determine what specifications the modulators must meet. Using the digital computer, graphical results were obtained which give the bandwidth for the component as a function of the modulation law parameters. The modulation laws considered were amplitude modulation, double sideband linear modulation, single sideband linear modulation, phase modulation, frequency modulation, compatible single sideband amplitude modulation, compatible single sideband phase modulation, and compatible single sideband frequency modulation. Also studied was the possibility of demodulating carriers by recovering the complex envelope of the modulated carrier and then extracting the message signal with a baseband post-processor. It was found that only 2 systems are practical. These were a combination of an envelope detector and a phase detector, and the combination of 2 homodyne detectors. The latter was found to be better. Signed, the Chairman. Chapter 1, Introduction. Problem Statement. Modulation is defined as a systematic alteration of a carrier wave in accordance to the message to be transmitted. The modulation law is the mathematical rule used to alter the carrier properties. The carrier and the modulation law are selected to make better use of the transmission medium. An optimum choice of a carrier waveform and a modulation law for every possible situation does not exist since there are many alternatives. Each modulation law requires a specific modulator circuit. This is a problem if it is necessary to have a transmitter capable of operating with various modulation laws without drastic modifications. A similar problem exists for the receiver. This dissertation proposes a solution to these problems with the concepts of universal modulation and universal demodulation. Universal modulation and universal demodulation are defined as techniques used to modulate and demodulate carriers, following different modulation laws with a 2-stage process that separates the modulation process into a part that depends exclusively on the modulation law and a part that depends only on the carrier waveform. The block diagrams of the proposed universal transmitter and the universal receiver are shown in Figure 1 and 1.2 respectively. The baseband preprocessor in the transmitter modifies the input message to produce a signal that, if applied to the carrier modulation, produces a modulated carrier that follows a prescribed modulation law. The carrier modulator is independent of the modulation law. The carrier demodulator and the baseband postprocessor perform the inverse operations at the receiver. 1.2 Historical Background. This section presents a literature review of previous work done by other researchers that is relevant to the research problem. The concept of complex envelope was popularized by Degunji and Bedrosian. Degunji is spelled D-U-G-U-N-D-J-I, and Bedrosian is spelled B-E-D-R-O-S-I-A-N. The concept of complex envelope was popularized by Degunji and Bedrosian as a technique to analyze modulated carriers. The relationship between the complex envelope and the complex variable theory was studied in detail by Bedrosian, Volcker, and Lockhart. The mathematical form of the complex envelope is well known for most types of analog modulation. The idea of combining amplitude and phase modulation was used by some authors to study new forms of modulation. The properties of the most common types of modulation laws are well known and are available from most communications theory textbooks. The newer types of modulation, like compatible signal sideband modulation, or CSSB, have been studied in detail by Glorioso and Brazil, Mazzo and Sauls, Kahn and Thomas, Couch, and others. There is still some controversy among researchers about the virtues and flaws of CSSB. The transmission bandwidths required for distortionless transmission or with tolerable distortion for the modulated carrier are all well-known properties. It is claimed that CSSB modulated carriers can occupy more bandwidth than their double-sided counterparts and that any bandwidth economy depends on the modulated parameters. Also known is the performance of these modulated carriers in the presence of noise. In the CSSB modulated carriers have a poor signal-to-noise ratio when detected with the receiver, for which they were designed to be compatible. The idea of designing a modulator capable of following various modulation laws have been proposed by Volcker, Lockhart, Couch, and Thomas. Volcker and Lockhart proposed a combination of phase modulator with an amplitude modulator. Couch proposed a combination of two balanced modulators to obtain different modulated carriers with the same general structure. Muizin proposed the independent modulation of the sidebands. Kane proposed modifications to an SSB transmitter to obtain CSSB modulated carriers. Woodhold and Thoney proposed the use of a two-dimensional semi-recursive filter to obtain some forms of modulation. The idea of a universal receiver has been suggested by those researchers working on the transmitter problem. Most effort has been channeled toward the development of optimum receivers for specific modulated carriers under specific restrictions, rather than to obtain generalized receivers. Non-optimum receivers are well known and are discussed in many communications theory textbooks. 1.3 Research Areas. Although the idea of universal modulation and demodulation is not new, little attention has been paid to the feasibility of such structures. This dissertation studies possible structures for the universal transmitter and the physical limitations imposed on the realizations. To achieve this goal, it is necessary to study the properties of the complex envelope components as related to the different modulation laws, which, to the author's knowledge, have not been studied before. This is the subject of Chapter 3. The universal transmitter is covered by Chapter 4. Here, various system block diagrams are proposed as universal modulators, and their bandwidth and parameter constraints are studied to determine their feasibility as practical systems. The receiver case is the subject of Chapter 5. The receiver is studied as an extension of the transmitter analysis, and general requirements are stated for the receiving problem. Finally, Chapter 6 states the conclusions and highlights the important results obtained throughout the dissertation. Chapter 2 Mathematical Preliminaries. Introduction. Any cosinusoidal carrier wave is completely described by its amplitude and the absolute phase angle. Consequently, there are only three distinct ways to modulate a carrier. 1. Modulate only the amplitude. 2. Modulate only the phase angle. 3. Modulate the amplitude and the phase angle simultaneously. The modulated carrier is described by the general expression y of t equals a of t cosine bracket 0 times t, where a of t represents the carrier amplitude, 0 times t represents the carrier absolute phase angle, and y of t is the modulated carrier. The function a of t is also known as the real envelope of y of t, or simply the envelope. The absolute phase angle is 0 of t equals w base o times t plus p of t, where the first term depends exclusively on the carrier frequency in radians per second and the time, and the last term represents relative phase angle with respect to cosine, and includes any other phase angle variations. That might have been omega, I don't know, they wrote it as a regular W. So. Polarization modulation by modulating the transversal components of radiated RF field will not be considered here. Modulated carrier is a minimum phase signal if negative radians is less than p of t is less than or equal to radians vector times t. It is defined as non-minimum phase otherwise. 2.2 The complex envelope. It is a well-known fact that a cosinusoidal waveform can be described in terms of a complex exponential using Euler's formula. And it goes on to list the equations. Analytical functions. A complex function is classified as analytic if the real and imaginary parts form a Hilbert pair. This means that the complex function s of t is an analytic function if Im in brackets S of t equals h in brackets re in brackets S of t, close brackets. This is the Hilbert transform of the argument, and Im and Re are the imaginary and real part operators. If S of t is an analytic function, the following properties are true. The Fourier transform of S of t vanishes for all negative frequencies. 2. The real and imaginary parts have identical autocorrelation functions. 3. The complex function is completely described by either the real part or the imaginary part. Any complex modulated carrier, Z of t, is not necessarily analytic. The spectrum of most types of modulated carriers is concentrated near the carrier center frequency and gradually drops to zero as the frequency approaches zero, and remains zero for negative frequencies. Under this condition, Z of t can be considered to be approximately analytic. The complex envelope is analytic if and only if V of w is identical to zero for all negative frequencies. This is satisfied whenever the complex modulated carrier is analytic and if at the same time Z of w is zero for all the frequencies in the interval 0 to w base 0. This type of modulated carrier spectrum is defined as single-sided spectrum. I think they're using W as omega, but it doesn't say, which is really frustrating. But anyway, continuing on. There are single-sided spectrums that do not satisfy Bedrosian's definition of analytic. A simple example is when S of t in equation 2-13 has a non-zero mean value. However, this case can be analyzed because the effect of the non-zero mean value can be considered separately. 2.4 Modulation Techniques. Modulated carriers can be classified in terms of 1. How the modulation law acts on the spectrum of the message. 2. The distribution of the spectrum of the modulated carrier. And 3. How the effect of the modulation is observed in the time domain waveform. A modulation law is defined as linear modulation if the spectrum of the modulated carrier is a translation of the spectrum of the message and if superposition applies. The modulation law is defined as nonlinear otherwise. The spectrum of the modulated carrier is classified as double-sided if it is non-zero over at least a finite frequency range on both sides of the carrier frequency. The spectrum is classified as single-sided when all the energy or power is concentrated in only one side of the carrier frequency. In the time domain waveform, modulation of the carrier can be accomplished by the systematic alteration of the carrier amplitude, the carrier phase angle, or both the amplitude and phase simultaneously. The following are types of modulation to be considered in this dissertation. In all cases, the message signal is assumed to be real analog signal. Amplitude modulation. In this case, the message signal is carried exclusively by the real envelope of the carrier. It is a translation of the spectrum of the message and the spectrum of a constant to the carrier center frequency. Due to the constant involved in the modulation process, the modulation law is nonlinear. The AM modulation carrier has a double-sided spectrum. Linear modulation, or LM, is a translation of the spectrum of the modulating signal to the carrier center frequency. This can be a mixture of the amplitude and phase modulation, and it can be single-sided or double-sided since both sidebands carry the same information. The single-sided version is known as single sideband linear modulation, or SSB-LM. And the double-sided version is called double sideband linear modulation, or DSB-LM. If the DSB-LM modulated carrier is linearly filtered by an asymmetrical bandpass filter centered around the carrier frequency, the output is classified as vestigial sideband linear modulation, FSB-LM. Angle modulation. The information is carried by the phase angle of the carrier, and it can be recovered from the zero crossing of the carrier. It is nonlinear. There are two main types: frequency modulation and phase modulation. In frequency modulation, the modulating signal is proportional to the derivative of the phase angle, while in PM, the modulating signal is proportional to the phase angle itself. Compatible single sideband, CSSB. The objective of CSSB modulation is to have a modulated carrier with a single sideband spectrum, while at the same time retain compatibility at the receiving end with the common types of double-sided demodulators. It is a mixture of amplitude and angle modulation and is nonlinear. There are various alternatives to achieve CSSB. This dissertation restricts its attention to SSB types of modulations whose complex envelope is an analytic signal. The three types to be considered are CSSB-AM, CSSB-PM, and CSSB-FM. Single parameters and properties. This section defines and discusses the properties and parameters that are of interest in this dissertation. A deterministic signal is completely described by the time domain waveforms or by its Fourier transform, if it exists. If the signal is produced by a random process, there are many possible time domain waveforms. This situation requires a more general description based on the statistical properties of the signal source. The autocorrelation function of the random process is a satisfactory description in most cases, but it may not be appropriate for nonlinear problems. The autocorrelation function of the random processes S of t is defined as R base S, parentheses t, comma, t plus tau, in parentheses, equals E brackets S of t times S times parentheses t plus tau, close parentheses, in brackets, where E is the expectation operator and S of t is the complex conjugate of S of t. So S times t is the complex conjugate of S of t. The expectation operator is defined as, and then it goes on to list the equation. 2.5.1 Bandwidth. Most signal processing problems involve filters. In some cases, the filter is required by the system realization. In others, it is present due to the circuit limitations. Therefore, it is necessary to determine the bandwidth required by the signal before the system components are specified. There are various definitions for bandwidth. The most frequently used definitions will follow. All definitions are in terms of hertz, Hc. 3 decibel down bandwidth, abbreviated BD. It is defined for a real valued signal as the frequency where the power spectral density function decreases by 3 decibels relative to the maximum level. This is the same as G of BD, or down bandwidth, equals half of max bracket G of F. In percent power bandwidth, abbreviated BP. It is defined for a real valued process as the frequency band that contains n percent of the total power in the signal. Equivalent noise bandwidth, abbreviated BN. The equivalent noise is the width of a rectangle with a height of G of 0 that contains the same area as the power spectral density curve. Equivalent filter bandwidth, B base F. The equivalent filter bandwidth is defined by the block diagram of the procedure used to calculate it rather than by a mathematical expression. This procedure is illustrated by figure 2.1. There are 2 signal paths, one through an ideal low-pass filter and the other through a delay line that compensates the delay introduced by the filter. The 2 signals are applied to the same kind of signal processor, and the 2 outputs are compared to determine the error introduced by the filtering action. The signal processor includes all processing done between the point where the bandwidth is measured to the point where the error is measured. Define the equivalent filter bandwidth as the width of the passband of the ideal low-pass filter that produces a determinate amount of error. The 3 decibel bandwidth is often used to specify the useful frequency range of amplifiers and filters. It should not be used to specify the bandwidth of a signal because it does not take into account the signal properties. The power bandwidth is useful in situations where the evaluation of the power distribution is the prime consideration. It has the disadvantage that equation 2-20 cannot be solved in the terms of B base P, except in a very few simple cases. Therefore, it must be calculated with a numerical iterative process. It does not specify the actual bandwidth required by a signal unless the power is the only consideration. The noise equivalent bandwidth and the second moment bandwidth have the advantage of being directly related to the statistical properties of the signal. The disadvantage is that if the signal is subsequently processed by a nonlinear system, the distortion introduced may not be simply related to these bandwidth definitions, although in most cases it is possible to relate the input bandwidth to the output bandwidth. Eberson found that the second moment bandwidth of an arbitrary zero-memory nonlinear transformation of a stationary random process is given. Here, let's see the equation. The equivalent filter bandwidth has the advantage of relating the actual bandwidth requirements of the signal at a point in the system to the criteria used to measure the performance of the system. Therefore, the equivalent filter bandwidth is the bandwidth required for the actual design at the point where it is measured. It has 2 disadvantages. The first one is that a closed-form expression is almost impossible to obtain. Therefore, it is necessary to simulate the system in order to calculate the bandwidth. This is not a great disadvantage if the reader realizes that all the other definitions may require numerical solutions in complicated cases. The second disadvantage is that the definition is based on a subjective consideration of what is a good performance criterion for a system. Therefore, universal acceptance of this definition cannot be expected. However, distortion is precisely what the design engineer will consider as a design criterion. Therefore, this definition is acceptable. A similar technique is often used to define the bandwidth of FM signals as a function of distortion. Even in the case of the second moment bandwidth, where an analytical expression may be found, the design engineer cannot use it directly as the design bandwidth without subjective considerations. Section 2.5.2 Dynamic Range. The voltage current dynamic range of an analog signal is defined as the maximum positive voltage or current and the maximum negative voltage or current that can be found in the signal under consideration. This is important because physical devices and circuits have definite maximum voltage or current levels that, if exceeded, may result in improper operations or physical damage to the components. The numerical dynamic range is defined for digital signals as the maximum positive or negative number that can be found in the signal sequence and the minimum number that must be resolved by the computing circuits. These numbers may determine if overflow or underflow will occur and how many bits are necessary to represent the sequence. Section 2.5.3 Measure of Error. There are two common measures of error. There are mean squared error and distortion. It involves knowledge of the statistics of the signal, so it is a widely accepted theoretical criterion of goodness of a system with regard to the mean squared error formula. Equation 2.29 can include the effect of noise and other disturbances, so the minimalization of the mean squared error is often the objective of optimization problems. The main disadvantage is that it is difficult to measure because any procedure used requires time delay equalization of x of t and x of t to guarantee that the measured e bracket e squared comes from x of t and not from the measuring procedure. The other measure of error is distortion. It is based on the selection of the deterministic test message that is used as the reference against which the distortion is calculated. Distortion is usually specified as harmonic distortion or intermodulation distortion. The total harmonic distortion is defined for a single tone test signal as, and he lists the formula. The intermodulation distortion definition takes into account the mixing of the test signal frequency components due to the nonlinearity. It includes the harmonic distortion, so it is usually higher than the THD. Since two tones are involved, there are many possible combinations of relative amplitudes and of relative frequency separation. There is no universally accepted standard. The typical arrangement is a 4:1 amplitude ratio and frequency ratio, but there is no technical reason for using it over any other combination. It is advisable to state clearly what is the test signal what is the test signal together with the distortion readings or calculations. From the engineer point of view, the distortion figures are easier to measure than to understand than the mean squared error because they are self-normalizing and no phase equalization is required. The disadvantage of the distortion definitions is that they do not take into account the effect of noise and other disturbances. Equivalence between continuous and discrete signals, section 2.6. In some situations, it is desirable to replace a continuous time signal with a sampled or discrete time version of it. If certain conditions are met, both representations contain the same information. Let x base a times w be the Fourier transform of the continuous time signal, and x base d times exp times jwt the discrete Fourier transform dft of the sampled signal. The star notation x of baseband d parentheses exp jwt is a common practice in digital signal processing literature. It is the result of evaluating the z transform of x of n of t with z equal exp of jwt. Summary. This chapter presented the definitions and the concepts that will be used throughout the dissertation. It also discussed the various alternatives to the definition of bandwidth in order to help select the best one of the particular application. Chapter 3. The Complex Envelope. Section 3.1 Introduction. The complex envelope is known to completely describe the modulation process since it contains all the message information. It is reasonable to assume that the generation of the complex envelope is all that is needed to produce a modulated carrier that follows any specified modulation law. This chapter presents a compilation of the complex envelope functions for well-known types of modulated carriers and analyzes some properties that have not been considered before in the literature. Since physical systems cannot handle complex voltages or complex currents, it is necessary to study the representation of the complex envelope in terms of real-valued functions. These components will be used in chapters 4 and 5 to study the possible structures of the universal transmitter and receiver. The general properties of the complex envelope are well known and were already presented in section 2.2. This discussion concentrates on the properties of the components that have received little attention in the literature. Any complex number can be represented geometrically as a point or a vector in the two-dimensional complex plane defined by the real and imaginary axis. The two most common descriptions of a complex function are in terms of absolute value and argument, and in terms of the two quadrature components. The quadrature components are equivalent to two orthogonal vectors that are the projections of the complex envelope vector along the real and the imaginary axis. Section 3.2, the complex envelope for different types of modulation. The general approach to obtain the equation of the complex envelope for a modulated carrier is to specify certain conditions that the modulated carrier must satisfy. Using available mathematical techniques plus some ingenuity, equations may be found that satisfy all or some of the conditions. These conditions usually require a specific relationship between the message signal and one of the complex envelope components and a specific characteristic of the modulated carrier. For practical purposes, one may like to specify three parameters, namely the magnitude, the phase, and the bandwidth occupancy of the modulated carrier. Unfortunately, there are only two components, therefore the arbitrary specification of the three requirements is not possible. Volcker developed and Lockhart expanded a theory that serves to study the complex envelope of modulated carriers where the message is a periodic waveform. It is based on the zero singularity patterns of the Z-transform of the complex envelope. By examining and manipulating the location of the zeros or singularities, it is possible to determine if the desired properties can be obtained or if they are not compatible. This section considers the types of modulation defined in Section 2.4. Section 3.2.1 Amplitude Modulation, or AM. By definition, amplitude modulation requires the modulated carrier to have a spectrum identical to the translation of the spectrum of the message, except for a carrier line, and the complex envelope to have a magnitude proportional to the message. Section 3.2.2 Linear Modulation, or LM. Linear modulation is the linear translation of the spectrum of the message to the carrier center frequency. This requires a complex envelope. V of t equals Cx of t. The spectrum is double-sided, so this is called double sideband linear modulation, or DSB-LM. The single-sided version is obtained by replacing the message with an equivalent analytical signal that has a spectrum identical to one of the sides of the spectrum of the message. This is the same as requiring the complex envelope to be V of t equals C brackets X of t plus J X of t brackets, where X of t is a Hilbert transform defined by equation listed in 2.2-14. This is known as single sideband linear modulation, or SSB-LM. Section 3.2.3 Angle Modulation. Angle modulation requires that the relative phase angle of the modulated carrier be a linear function of the message. Phase modulation, PM, requires that the relative phase angle, P of t, be directly proportional to the message, while frequency modulation, FM, requires that the message be proportional to the derivative of the phase angle. The constant d base p and d base f are the PM modulation index and the FM frequency deviation constant. Section 3.2.4 Compatible Single Sideband Modulation, or CSSB. The idea behind compatible single sideband modulation, or CSSB, is to obtain a modulated carrier that is compatible with receivers for conventional AM, PM, and FM, while at the same time obtain the bandwidth savings of a single-sided spectrum. This requires the selection of A of t in the CSSB AM case, and P of t in CSSB-PM and CSSB-FM cases. This leaves only one function to specify. This function should result in a single-sided spectrum that at the same time is narrower than the spectrum of the conventional case. This may not be possible in all cases. Several solutions have been proposed for the CSSB-AM signal by Villard, Kahn, Bedrosian, Powers, and others. The Villard system has been shown to be non-band limited and not completely single-sided. The power system is absolutely band limited and single-sided, but it is not exactly compatible with conventional AM receivers. Cons and Bedrosian systems are very similar and have single-sided spectrums, but they have been shown not to be absolutely band limited. These systems do show some effective bandwidth reduction compared with the double-sided cases, but the reduction depends on the message level. Solutions to the CSSB-FM and CSSB-PM cases have been proposed by Bedrosian, Glorioso in Brazil, Mazzo and Salles, Kahn and Thomas, Dubois and Augard, and Barnard have studied the CSSB-PM and CSSB-FM carrier spectral properties. It is known that CSSB-PM and CSSB-FM require less bandwidth than conventional PM and FM for low modulation levels, but that the bandwidth reduction depends on the modulation level. Bedrosian also showed that if an analytic periodic signal, S of t, is used to form the complex envelope, V of t equals C, exp bracket S of t, end bracket, a single-sided complex envelope results. Couch showed that other SSB signals could be obtained by the use of entire functions to obtain analytic complex envelope functions. Section 3.3, Autocorrelation function of the complex envelope components. This section presents the autocorrelation function of the complex envelope and derives the autocorrelation function of the components for different types of modulation laws. If the autocorrelation function is available, the second moment bandwidth can be calculated using equation from section 2-24. Section 3.3.1, General expressions for the autocorrelation function. This section lists the equations. The next section also lists all equations, and that section is 3.3.2, Special Case Analytic Complex Envelope, along with equations on AM and equations on DSB-LM. Those are both skipped in this reading. Section 3.3.7 FM section is skipped over the equations. And we pick up on Chapter 4, the Universal Transmitter. Section 4.1, Introduction. This chapter presents the idea that a transmitter can be designed so that it is capable of producing almost any type of modulated carrier. The general structure of the transmitter was already shown in Figure 1.1. First, the complex envelope is generated from the message and in the modulation law. The complex carrier is subsequently modulated with this complex envelope. The real part is extracted and amplified. This is a universal transmitter since the baseband processor can be programmed to implement the desired modulation law. The block diagram of this system is shown in the figure. The system proposed in the previous paragraph is unrealizable because it requires the generation of complex valued voltages. A complex function can be described by real valued functions, so by manipulation of the different representations of the complex envelope specified by the operations illustrated in Figure 4.1, a physically realizable system can be obtained. In a practical transmitter, it is always possible to separate the power amplifier from the actual modulator circuit if a linear amplifier is used. Since amplification is a linear operation, nothing is lost in the analysis if the power amplifier is disregarded. This system without power amplification will be defined as the universal modulator. Section 4.1.1 The complex envelope as a vector. It is well known that a complex valued function can be represented as the trajectory of the tip of a vector in the two-dimensional plane described by the real and the imaginary axis. A vector in a two-dimensional plane can be described in terms of its phase angle and its magnitude, or in terms of a linear combination of two non-parallel vectors. Four of these possibilities are illustrated in Figure 4.2. The polar representation consists of the magnitude A of t and the phase angle P of t. The quadrature components are two orthogonal vectors that represent the quadrature functions I of t and Q of t. These are the conventional representations for a complex valued function and correspond to the sketches shown in Figure 4.2. There are two more representations that are a direct consequence of the vector representation. The linear combination of two non-orthogonal vectors is shown in Figure 4.2. Here, the magnitudes of the two vectors are adjusted to represent the complex envelope vector while their phase angles remain fixed. In the last case illustrated by Figure 4.2, the length of the vectors remain constant and the phase angle is adjusted. These equivalent representations will generate the same complex envelope, but certain representations may have economic advantages in terms of circuit realization energy consumption. Section 4.1.2 Physical Modulators. This section is concerned with the models for the physical modulators. It is necessary to understand the modulator limitations in order to take them into account in the design. The function of the modulator is to alter the properties of the carrier in accordance to the modulating signal. Ideal modulators do just that, but practical modulator circuits have definite maximum input levels and a limited frequency response. If the maximum input level is exceeded, the circuit may not operate as intended or the circuit is damaged. The effect on the modulated carrier is distortion or no carrier at all. The limited frequency response must be taken into account because if the modulator circuit cannot follow the modulating signal, the signal modulated into the carriers is different from what it is supposed to be. The limitations on the maximum input level on the frequency response can be modeled as a saturating amplifier and an ideal low-pass filter, respectively. The modulator can be approximated as the cascade combination of these two blocks, followed by an ideal modulator. There are two possible arrangements that are not equivalent. The final selection depends on which model describes better the modulator under consideration. It is possible that the maximum input level might be frequency dependent or that the frequency response might be input level dependent. In these cases, a new model is necessary. Signal levels can be attenuated, so the maximum input level problem can be solved in cases where the message does not have such a large dynamic range that circuit noise becomes a problem. The solution to the frequency response problem is not that simple because there is no way of reducing the bandwidth occupied by a signal without changing the signal itself. This means that the modulator model can be simplified to the cascade combination of an ideal low-pass filter and an ideal modulator. There are two basic modulators. There are the amplitude modulator and the phase modulator. The ideal modulator is defined by the following equation, and the equation is listed. Ka is the carrier peak amplitude in the absence of a modulating signal. Kb is a modulator constant. Wo is the carrier frequency, and Yt is the modulated carrier. A balanced modulator can be used in place of an amplitude modulator if a constant is added to the input. The phase modulator can operate as a frequency modulator if the minimum phase condition is lifted. If the modulating signal has a zero mean value, the frequency modulator can replace a phase modulator with a differentiator at the input. If the modulating signal has a non-zero mean value, the differentiator will destroy the mean value. ROWE, R-O-W-E, considers in detail the relation between the FM and PM functions and their power spectral density limitations. The AM-PM modulator. The first structure to be considered to serve as a universal modulator is the AM-PM modulator. It consists of a phase modulator followed by an amplitude modulator together with a pair of baseband preprocessors. The baseband preprocessor number 1 generates A of t, while the baseband preprocessor number 2 generates P of t. Section 4.1.4, the quadrature modulator. The arrangement of two balanced modulators in phase quadrature is well-known method generation, SSB-LM. The idea has been extended to other types of modulation by Thomas and others. The block diagram for the quadrature modulator is shown in figure 4.6. It is desired to generate equation 2-7 with complex envelope quadrature components. So the baseband preprocessor number 3 has to generate I of t, while the baseband preprocessor number 4 generates Q of t. The I of t and Q of t functions will be defined as the quadrature components. These quadrature components are related to the inputs of the balanced modulators. The PM modulator. The idea of combining two phase modulators to generate an AM carrier was proposed by Chireix, Chireix. This system is marketed by RCA under the trademark Ampliphase, AMPLIPHASE, Ampliphase. The same idea can be extended to generate other types of modulation. If figure 4.2 is examined, it is seen that the complex envelope can be obtained by adding two constant amplitude vectors with a specified phase arrangement. This is equivalent to the addition of two phase modulated carriers with constant amplitude. The block diagram of the proposed system is shown in figure 4.7. The details will be worked out later. Section 4.1.6, Other Configurations. It is possible to obtain the complex envelope by combining two vectors that are not orthogonal, as shown in figure 4.2. Part D. The required block diagram of a system like this is similar to the block diagram for the quadrature universal modulator, except that the carriers going into the balanced modulators are not in phase quadrature. Each vector 1 of t and u of t, 2 of t, can be written as a linear combination of I and q, and let ki and kq be unit vectors in real and imaginary axis directions then. And it goes on to list the equations. This non-orthogonal representation has a serious disadvantage. The magnitude of the vectors is never greater than the magnitude of the vector field. The magnitude of vector 1 and 2 can be several times larger than the magnitude of the vector field as shown. This can be avoided with a slight modification. For example, 0 degrees and 90 degrees. This results in quadrature modulator, which has been considered before. Meewezen, Meewezen, proposed a system where the modulation process is done by independent modulation of the sidebands. This will be shown to be similar to the quadrature universal modulator. The complex envelope is obtained as the combination of the two functions. These two signals are single-sided, therefore they are analytic, so each one can be described as, and it lists the equations. This means that the analysis done for the quadrature modulator can be applied to Meewezen's approach to modulation. The block diagram of this system is shown in Figure 4.8. Observe that only I and Q have to be obtained, that the system requires two single sideband LM modulators, and that a Hilbert transform is necessary. The complexity of such is not compensated by any advantage over these other systems under consideration. For this reason, this will not be considered in detail. Kane studied the generation of CSSB modulation with a SSB-LM transmitter. This is similar to the Meewezen's approach if only one sideband is modulated. Section 4.1.7 Criterion for comparison and evaluation of the modulators. The two main criteria for comparison are the bandwidth required by the signals and their dynamic range. These are the two most important factors to consider in the design, and it is important to study their effect for different types of modulation laws. The point where the signal will be studied is at the output of the baseband preprocessor. These are the reasons to justify that selection. 1. This is the point where all modulation type dependent signal processing ends and where the signals go to the modulation law invariant part of the system. 2. This is the point where digital to analog DA conversion is most likely to take place. And 3. At this point, the signal bandwidths are independent of the properties of the actual circuits that will be used to build the baseband postprocessor or the modulators. The modulation parameters and the message signal have influence on the bandwidth of the complex envelope component functions and their dynamic range. In addition, the mathematical definition of these components may impose additional constraints that must be considered. Bandwidth was defined in 5 different ways in section 2.5.1. The definition to be used in this discussion is the equivalent filter bandwidth because it is directly related to the actual bandwidth required for the system. The measure of error is the intermodulation distortion, or IM, at the output of an ideal receiver in the absence of noise. The analysis and calculations will relate the bandwidth of the complex envelope components at the output of the baseband preprocessor to the distortion of the message at the receiver. The method to be used to calculate the IM distortion is best illustrated by Figure 4.9. There is a control signal that is obtained from the output of the baseband preprocessor modulated and demodulated by the receiver. The spectrum of the demodulated control signal is calculated to detect any nonlinearities acting on the message signal. Ideally, the IM distortion should be 0. In practice, it is non-zero due to the round-off errors and aliasing of sampled signals. The control signal is considered acceptable if the IM distortion is less than 0.0005%. The signal whose bandwidth is to be measured is filtered by an ideal low-pass filter, and from there on it follows the same path as the control signal. It is necessary to perform 3 different tests because 2 complex envelope components are involved. For example, the first test consists of filtering A of t and combining it with the control component, P of t. The second test reverses the situation, that is, A of t is the control component. The third test involves filtering both A of t and P of t. The purpose of the test is to determine if the AFT or PFT requires more bandwidth than the other, and to check what will happen if both components are filtered simultaneously. The test signal consists of two tones with equal amplitudes, but at two frequencies, F1 and F2, that are not harmonically related. The intermodulation distortion is calculated following equations. 2.31, but instead of including all of the frequencies to infinity, it is modified to include all components up to the third harmonic of the first order intermodulation product, F1 plus F2. The test message signal is shown in figure 4.1. The frequency scale is easily changed to represent other tones that have the same frequency relationship. Since the signal is deterministic, the peak amplitude is normalized to unity, so the modulation parameters take care of the denormalization. For Gaussian random signals, the theoretical peak amplitude is infinite, so it is necessary to normalize the variance and ignore those amplitudes that exceed a given level, for example, 5 times the standard deviation. Another consideration in measuring bandwidth is that there are cases, CSSB-AM is an example, where one of the complex envelope components, P of T in this case, is ignored by the ideal receiver in the noiseless case. The purpose of this neglected component is to produce a single-sided modulated carrier. The effect of filtering this component is reflected as incomplete sideband suppression and can be measured as the ratio of the power in the unwanted sideband to the total power expressed as a percentage. This is given by the following equation, and the equation is listed as S of percentage equals P base U divided by P base T times X 100%, where P base U is the power present in the suppressed sideband, P base T is the total power, and S% is defined as the sideband suppression factor expressed as a percentage. The calculation of the intermodulation distortion and the suppression factor were obtained with a computer simulation of the system shown in figures 4.6, 4.7, and 4.8. This requires the use of discrete signals to represent continuous signals. This was discussed in sections 2.6. To avoid errors due to aliasing or non-band limited signals, the control signal is monitored and the sampling rate is adjusted to reduce the distortion to acceptable levels. The results obtained in Chapter 3 for the complex envelope components, their autocorrelation functions, and the second moment bandwidth are used to check the reliability of the calculations. They are not directly applicable because these autocorrelation functions were derived for the special cases of a zero-mean Gaussian random process. However, the same general properties have to apply. The AM-PM modulator. This section analyzes the AM-PM modulator whose block diagram is shown in figure 4.5. This system was described in section 4.1.3. The mathematical expressions for the transfer characteristics of the baseband preprocessors number 1 and number 2 are the same as the equations obtained in sections 3.2 for the magnitude and phase of the complex envelope. These functions are summarized on table 4-1. Section 4.2.1 Bandwidth Requirements. The bandwidths required for the signals AFT and PFT are defined in terms of the equivalent filter bandwidth. These are calculated following the procedure outlined in section 4.1.5. The equivalent filter bandwidths of the AFT and PFT functions for AM, PM, and FM are easily calculated. The only nonlinearity is the addition of a constant in the AM AFT function. In these cases, the equivalent filter bandwidth can be defined for zero distortion at the receiver. This is achieved whenever the ideal low-pass filter shown in figure 4.9 is at least as wide as the message absolute bandwidth B. For the cases under consideration, the equivalent filter bandwidth is B. In practice, all signals are considered to be band limited. In the DSB-LM and SSB-LM cases, the computer simulation of the system is necessary due to the complexity of the analysis. The computer program used in the simulation is listed in Appendix B. The results of the simulation are presented as a graph that indicates the relationship between calculated intermodulation, distortion, and the equivalent filter bandwidth. The plots for the AFT and PFT components for DSB-LM and SSB-LM are shown in Figure 4.1. The bandwidth scale is normalized with respect to the message equivalent filter bandwidth. These plots were obtained for the case where one of the two components is filtered and the other is taken from the experimental control signal. The cases where both AFT and PFT are filtered are very close to the plots for the filtered phase alone. These plots indicate that the SSB-LM phase function requires the widest bandwidth of all the modulation types under consideration. The reason for such a large bandwidth is that PFT exhibits phase jumps in the SSB-LM and DSB-LM cases. In the CSSB cases, there is usually a component that is ignored by the receiver. For example, CSSB-FM is detected by an FM receiver that ignores any amplitude modulation present in the carrier. This component is necessary to obtain a single-sided modulation carrier. Therefore, its bandwidth must be determined. The PFT function for CSSB-PM and CSSB-FM and the AFT function for CSSB-AM are identical to the PM, FM, and AM cases already considered. Instead of trying to measure the distortion in the unused component, it is better to measure how this component affects the undesirable sideband suppression. The procedure was outlined in Section 4.1. The sideband suppression factors S% for all the single-sided carriers under consideration are presented as a function of modulation parameters in Figures 4.1 through 4.5. Again, the SSB-LM phase function demands more bandwidth than all other cases under consideration. This is expected because a large distortion figure was obtained at the output of the receiver, indicating that the real part of the complex envelope is distorted. Therefore, it is reasonable to expect that the imaginary part is also distorted, and the resulting complex envelope is far from being analytic. The plots for FM and CSSB-FM are in terms of D, the deviation ratio, defined as D equals F base D divided by B equals D base F divided by 2 radian B. Where F of D is frequency deviation in hertz, B is the message bandwidth, and D base F is the frequency deviation in radians per second. The CSSB plots for the sideband suppression factors are presented in Figures 4.13 through 4.15. These curves now show equivalent filter bandwidth normalized with respect to the message bandwidth is related to the modulation constraints when the sideband suppression factor is used as a parameter. These modulation constraint constants are the AM modulation index in the CSSB-AM case, the PM modulation index in the CSSB-PM case, and the FM deviation ratio in the CSSB-FM case. These modulation constants were defined in equations 3-3-3-31 and 4-35 respectively. The bandwidth requirements increase with the modulation parameters. In the worst case, an equivalent filter bandwidth of 2 or 3 times the original message bandwidth is satisfactory. The equivalent filter bandwidth requirements of all the cases considered in this section are summarized on Table 4-2. Section 4.2.2 Dynamic Range. Since physical modulators have definite maximum input levels, it is clear that the modulation parameters may be constrained to a particular range. Let E base B and E base P be the maximum input allowed to the balanced modulator and the phase modulator respectively. Using equations, it is clear that the maximum values allowed for A of T and P of T are max bracket A of T close bracket less than or equal to K base A, E base B, and max bracket P of T close bracket less than or equal to K base C, E base P, where K base C and E base P is maximum phase shift produced by the phase modulator. Assume that the message is normalized to unit peak amplitude, the constraints on the unmodulated carrier amplitude C, and the modulation parameters can be found by substituting the expressions listed in Table 4-1 for the A of T and P of T functions. The equations are listed, and we pick up at section 4.3. Quadrature modulator. The quadrature modulator is illustrated in 4.6 figure. The expressions for the transfer characteristics of the baseband preprocessors number 3 and number 4 are similar to the equations obtained in Chapter 3 for the quadrature function components of the complex envelope. These equations for the baseband preprocessor are listed in Table 4-3. Section 4.3.1 Bandwidth Requirements. The bandwidth requirements for the signal I of T and Q of T are described in terms of the equivalent filter bandwidth, which was defined in Section 2.5.1. The bandwidths are calculated following the procedure outlined. The equivalent filter bandwidth of I and Q are easily calculated for the AM, DSB-LM, and the SSB-LM cases. The bandwidth can be defined for zero distortion if the ideal low-pass filter shown in Figure 4.9 is at least as wide as the absolute bandwidth of the message, B. In these cases, the equivalent filter bandwidth is B. Section 4.4.1 Bandwidth Requirements. In this section, it is only necessary to study the bandwidth required for phase of T because the P of T case has already been studied in Section 4.2.1 for the AM-PM modulator. Preliminary work showed that when both phase of T and P of T were filtered, the resulting distortion curve was about the same as the highest distortion produced by the individual components. For this reason, the case where both components are bandwidth limited is not studied in detail. There is a parameter that must be watched with care. It is the ratio 2L over C that appears as part of the argument of cosine raised to the negative 1 times the period. The argument of cosine to the negative 1 times the period must be in the range negative 1, 1. Where the function is not defined. This can be satisfied if the argument is assigned a value of 1 whenever it is larger than 1 and negative 1 whenever it exceeds negative 1. But this causes clipping of the signal in the argument of cosine negative 1 times the period, and distortion is observed at the receiver. If the value of the argument never exceeds these limits, the ratio of 2L over C has little effect in the equivalent filter bandwidth. A ratio of 4 was selected for all the calculations except for CSSB-FM, where a ratio of 16 was used in order to increase the deviation ratio range so that it can be compared with other case studies before. This ratio of 16 is too high for most applications because the phase modulator will have to be handled 64 times the power of the unmodulated carrier. Observe on Table 4-5 that AM and CSSB-AM have the same phase of T function. This means that they can be considered together. The relationship between the required equivalent filter bandwidth and the AM modulation index is shown as a graph in Figure 4.26. A line can be drawn to approximate the required equivalent filter bandwidth. The ideal receiver ignores the amplitude of the CSSB-PM and CSSB-FM modulated carriers. If there is no clipping in the argument of cosine raised to the -1 times the period, the phase of T function has no effect at all at the receiver, but it determines how the power is suppressed in the undesirable sideband. This is illustrated by figures 4-29 and 4-30 for CSSB-PM and CSSB-FM respectively. For D base P larger than 0.8 and D larger than 1.6, the curves show a fast increase in the slope indicating that clipping is taking place. The PM and FM phase functions are constant, so the bandwidth is 0. The bandwidth requirements are summarized in Table 4-6. The critical bandwidths obtained for the DSB-LM and the SSB-LM PFT functions. Therefore, from the bandwidth requirements point of view, there is little difference between AM, PM, and PM modulators. 4.4.2 Dynamic range. The ratio of 2L/C is important in determining the dynamic range of the modulation parameters in the phase function. The dynamic range of the parameters in the P of T function were already discussed with the AM-PM modulator. The basic restriction imposed in the phase function is due to the definition of cosine raised to the -1 times period. The lower limit is always satisfied since A of T is always positive. So, this means that the results derived for the AM-PM modulator A of T function in section 4.2.2 can be used if K base A, E base B is replaced by 2L. And it goes on to list the equations. 4.5 Discussion of results. This section discusses the results obtained in sections 4.2.4.4 for the three universal modulators under consideration. The bandwidths were defined in terms of the equivalent filter bandwidth, which was defined in section 2.5.1. The test message was selected to produce IM distortion figures that are higher than those that would be obtained with the usual 4:1 amplitude ratio because it is necessary to make allowances for practical baseband preprocessors where the operations itself introduce more distortion. Practical baseband preprocessors may have transfer characteristics that are not a perfect reproduction of the mathematical equation. The synthesis of the transfer characteristics may require that approximations of functions and mathematical operations in order to reduce circuit complexity or to handle physically unrealizable operations like division by zero or the Hilbert transform. These approximations result in additional distortion that has not been considered in the analysis because the distortion is produced by the specific baseband preprocessor realization and is not due to the complex envelope component's characteristics. In this work, all the functions and transformations were assumed to be ideal. The second moment bandwidth is not used extensively because, 1, it cannot be obtained in closed form for all cases. 2, some of those cases where it can be obtained are restricted to 0, meaning Gaussian noise with specified autocorrelation functions, and 3, it can be misleading. The third reason is very important. Consider the second moment bandwidths calculated for the DSB-LM phase function and for the PM real quadrature component. These are given by equation 3-136 and equation 3-149. Compare with figures 4.11 and 4.16 and observe that to get the bandwidth definitions to agree with 0.1% distortion curve, it is necessary to add 3B to the PM case and about 8B for the DSB-LM case. This is inconsistent with once rigorous second moment bandwidth has been transformed into a partly arbitrary definition that must be checked against distortion anyway. For this reason, the second moment bandwidth is not very useful for nonlinear problems. This bandwidth definition is not completely useless since it serves as a guide of how the different modulation parameters affect the bandwidth, and it serves to confirm the simulation results. The reason why the second moment bandwidth fails to be consistent if compared with the equivalent filter bandwidth is, and how the different frequency regions of spectral distribution are used to obtain the final signal. This spectral distribution can be completely altered by nonlinear processing. The second moment bandwidth definition ignores the fact that the energy above B base S may be important as the reconstruction of the message. How important this energy is depends on the specifics of each case. 4.5.1 The AM-PM modulator. The block diagram of the AM-PM modulator was presented in figure 4.5. Baseband preprocessors transfer characteristics, the A of t and P of t functions bandwidth requirements, and the dynamic range constraints were presented in section 4.2. The critical modulation laws were the DSB-LM and the SSB-LM. These cases required phase functions with a bandwidth of 16B and 180B respectively, while their magnitude functions require less than 10B and 5B respectively. For 0.1% IM distortion, the curves for P of t in figure 4.1 indicate that the spectrum of the phase functions is a wideband, which agrees with discussion in sections 3.4.2 and 3.4.3. The plot for the SSB-LM indicates that the significant frequency component of P of t decay rapidly after 200B. The CSSB cases show no relationship between the distortion at the output of an ideal receiver and the bandwidth. The ideal receiver uses only one of the two complex envelope components, and this component was simply related to the message signal. The unused component was necessary to obtain a single-sided carrier, but even for the 0.01% of the power in the undesirable sideband, the bandwidth requirements were not strict. The single sideband -LM, A of t, and P of t functions were also affected the undesirable sideband suppression, but the necessary bandwidth was below that required for low distortion reception. The advantage of the AM-PM modulator over the other two systems is that it is well suited for AM, PM, and FM generation. The main disadvantage is that it is impractical as a SSB-AM modulator. For example, for a message with a 5 kHz bandwidth, the phase modulator must be capable of handling at least 1 MHz input modulating signal. The baseband preprocessor also has to compute the quotient x of t over x of t, which is troublesome if x of t is 0 or nearly 0. The AM-PM modulator can be improved. Observe that the balanced modulator allows negative polarity inputs, therefore, instead of generating A of t for DSB-LM, generate I of t for DSB-LM. If this is done, P of t is 0, so the DSB-LM problem is quickly solved. The SSB-LM case still remains a problem. Section 4.5.2, the quadrature modulator. The block diagram of the quadrature modulator is shown in Figure 4.6, Section 4.3 discussed the details of equations for transfer characteristics and obtained the bandwidth and dynamic range constraints. In this system, there were no critical cases, although most functions require more bandwidth than the message. None of the cases were under study required more than 9 times the bandwidth of the message. The largest bandwidths were required for the CSSB-PM and the CSSB-FM components. When the CSSB components were considered individually, they require more bandwidth than their double-sided counterparts. If both components were filtered with the same kind of filter, the required bandwidth was less or equal to that of the double-sided case. This reduction seems to be due to distortion cancellation caused by built-in redundancy of the quadrature components because they form a Hilbert pair. The second moment bandwidth fails to predict this effect. This kind of bandwidth reduction was not observed in the double-sided cases where both components were filtered. The distortion was the same as the highest of the two distortion figures for each individual component. The single-sided property of CSSB was not affected when both components were filtered to the same bandwidth. The reason for this is that this kind of filtering preserves the Hilbert pair relationship, therefore the complex envelope remains analytic. The dynamic range constraints on the modulation parameters were found to be the same or more liberal than those required by the other two systems. The advantages of this system were: 1. The restrictions on the dynamic range were less restrictive than in any of the other two systems under consideration. 2. SSB-LM was easily obtained. And 3. The bandwidths required were never more than 2 or 9 times the bandwidth of the message. The disadvantage of the quadrature modulator was that its baseband preprocessors tended to require more operations than the other two systems. Section 4.5.3 The PM-PM modulator. The block diagrams of the PM-PM modulator were shown in figures 4.24 and 4.26. The last block diagrams was preferred because it was less restrictive on the phase modulators. Unfortunately, it required 3 phase modulators. Both realizations required the same baseband preprocessors. The bandwidth requirements, the equations for the preprocessors, and the dynamic range limitations were discussed in section 4.4. The PM-PM modulator and the AM-PM modulator have similar limitations because they share the same P of t function. The phase of time function required slightly more bandwidth than the corresponding A of t function. The dynamic range constraints for the PM-PM modulator were found to be the same as those obtained for the AM-PM modulator, provided that the maximum input to the baseband modulator, K base A, E base B, be replaced by twice the amplitude of the carrier going into one of the PM modulators. The principal advantages of this system over the others was that the use of the two-phase modulator can be more efficient than an amplitude modulator or a balanced modulator because it allows Class C amplifiers. The disadvantage was the same as for the AM-PM modulator, plus the fact that the phase of t function requires more operations than the A of t function. Section 4.5.4 Which one is better? If versatility is the prime consideration, the quadrature modulator seems to be the winner. The bandwidth requirements were not excessive or unreasonable. The dynamic range constraints were always equal to or more liberal than those for the AM-PM and PM-PM modulators. For example, no restrictions are placed on the maximum phase deviation for PM and PM, while the AM-PM and the PM-PM modulators require the phase deviation to be restricted to plus or minus 180 degrees. The quadrature modulator was the only system under consideration capable of operating as a single sideband-LM modulator without extraordinary bandwidth requirements. When power efficiency is the main consideration and single sideband-LM is not needed, The PMPM modulator is more attractive because it allows the use of Class C power amplifiers. The AM/PM modulator is better suited for applications where simplicity of the design is principal concern. It is clear from the discussion that the final selection depends on the application. Section 4.6 Physical Realization of the Baseband Preprocessors. There are three basic alternatives to build the baseband preprocessors. There are 1. Continuous time, 2. Discrete time, continuous amplitude, 3. Discrete time, discrete AM amplitude. The main objective is to obtain a circuit that will perform satisfactorily the operations required by the entries on tables 4-1, 4-3, and 4-5. The actual design of the circuits depends on the state-of-the-art of the circuit design, and it will not be considered in detail. Section 4.6.1 Continuous Time. The continuous time realization involves the use of analog function generators, analog filters, multipliers, and other operational building blocks. It is necessary to account for and compensate time delays and phase shifts introduced by the different signal paths. This is especially important when the Hilbert transforms is involved because it is basically a 90-degree phase shifter. The baseband preprocessors can be built as separate circuit boards that are simply plugged in a main board that contains the modulators. The disadvantage of the continuous time realization is that analog function generators tend to change their characteristics with temperature and aging of components, so calibration may be necessary. Any deviation of the baseband preprocessor transfer characteristics from the ideal equation will result in additional distortion at the receiver or incomplete sideband suppression. Section 4.6.2 Discrete time continuous amplitude. This approach involves sampling the signals and using charge-coupled devices, or CCD, as valuable delay lines to simulate linear filters and phase shifters. The nonlinear operations must still be handled by analog circuits. Therefore, this approach may not be any better than the continuous time. The advantage is that propagation time delays are easier to compensate because they occur in discrete steps. Section 4.6.3 Discrete time, discrete amplitude. This is basically a digital approach. The continuous time message is converted to a digital sequence. The sequence is processed and the resulting sequence is converted back to a continuous time signal. Since this process involves sampling, it is necessary to know the bandwidth of the signals to be converted to digital sequences in order to avoid distortion introduced by aliasing. The equivalent filter bandwidth for the individual components can be used as a guide to determine the sampling rate since it shows the relationship between forcing a signal to be band limited and the resultant distortion. A proposed realization of an arbitrary baseband preprocessor is shown in Figure 4.31. The input low-pass filter is analog and its function is to limit the bandwidth of the input signal before sampling. The analog to digital converter, or AD, changes the band-limited x of t to a digital sequence, x of n of t, where n is the sample number and t is the time between samples. The digital computing network calculates the output sequence, r of n of t, following the baseband preprocessor transfer characteristic, and this sequence is converted back into a continuous time signal by a digital to analog converter. The output low-pass filter is necessary to equalize the transfer function of the D to A converter. The time-based coordinates the transfer of data between the different blocks. The digital computing network is the only part of the system that really depends on the desired transfer characteristic for the baseband preprocessor. Studying the entries of tables 4-1, 4-4, and 4-7 is apparent that all functions share a common computational structure. For example, the A of t function requires x of t, and then a nonlinear operation involving the angled x of t and then x of t. The Hilbert transform is a linear operation and it can be obtained with a digital filter. The message function x of t must be delayed so that the angled x of t and the x of t have the same phase relationship. The analysis done in section 4.2.1 revealed that A of t requires more bandwidth than the input message. This means that the sampling rate must be increased to prevent aliasing when the sequence is converted back to the continuous time signal. The interpolator is defined as a digital system that increases or decreases the sampling rate. If this analysis is extended to the other functions, p of t, phase of t, I of t, and q of t, a general block diagram of figure 4.32 is obtained. This block diagram ignores the possibility of sharing component blocks between baseband preprocessors because that depends on the actual function to be obtained. The low bandwidth requirements of the quadrature modulator makes it particularly attractive for the discrete time realization. Among the other things that must be taken into account in the discrete time, discrete amplitude realization are the number of bits per sample, the numbering system, and the time required to compute an output data point. The time required to compute a data point is important because everything must be done in real time, or at least with a finite time delay. The advantages of this realization are: 1. It is easier to obtain most of the required functions because these functions can be computed by numerical methods. 2. It is easy to account for time delays because of the discrete nature of time. 3. The system constants are unaffected by time or temperature because they are stored in numbers. And 4. The baseband preprocessor can be reprogrammed to generate other functions that fit the same general structure without actual circuit changes. The disadvantages are principally the accuracy and the speed of the computing circuit. 4.7 Summary. This chapter analyzed various alternatives to achieve a universal transmitter. It was shown that only two, the AM-PM and the quadrature transmitters, are really different. A third system, the PM-PM transmitter, was found to be similar to the AM-PM modulator in most respects. The transfer characteristics of the baseband processors, the bandwidth requirements for the component signals, and the dynamic range limitations were discussed in detail. The quadrature modulator was found to be the best of the three systems under consideration. But the other two systems have their particular advantages that may make them more attractive in some applications. Also discussed was the fact that the second moment bandwidth is not the best bandwidth definition for systems where nonlinear operations are involved and where the primary consideration is distortion. This was illustrated with examples that showed inconsistencies between distortion measurements and the second moment bandwidth. Finally, some possible realizations for the baseband preprocessor were discussed. The discrete time, discrete amplitude realization was found to be particularly attractive because it allows the possibility of obtaining the transfer characteristics of the baseband preprocessor in terms of software instead of hardwired circuits that are difficult to modify. Chapter 5, The Universal Receiver. 5.1 Introduction. The preceding chapter discussed the possibility of building a transmitter capable of generating different kinds of modulated carriers. It was shown that there are structures that can accomplish this. The chapter is concerned with the possibility of building a receiver capable of demodulating almost any carrier. The general structure of the receiver was shown in Figure 1.2. The objective is to find block diagram structures that can demodulate a carrier following a two-step process. One part of the process is independent of the modulation law and recovers the complex envelope of the input. The block diagram of such system is shown in Figure 5.1. The input-tuned RF amplifier acts as a bandpass filter and is necessary to limit the amount of complex noise, or N of T, going into the receiver. The filter must be wide enough to let the complex modulated carrier, Z of T, go through without noticeable distortion. The carrier demodulator extracts the complex envelope by multiplying Z of t plus N of t by the complex carrier exponential times negative j omega base 0 times t. This results in a baseband signal that is used by the baseband postprocessor to estimate the message signal, or x of t. The proposed system is physically unrealizable because it involves complex signals, but it can be made physically realizable if the complex signals are replaced by their real-valued components. For the discussion that follows, it is assumed that the system is studied after the input RF amplifier. The remaining system will be called an universal demodulator. The demodulator analysis is more complicated due to the presence of various disturbances like noise, fading, Doppler frequency shifts, multipath propagation, interference, etc. The receiver may have to be synchronized with the transmitter, which is not always possible. To simplify the analysis, the effect of synchronization and noise will be studied separately. 5.1.1 Demodulation as the inverse of modulation. The received complex modulator carrier is Z base R of t equals kz of t plus n of t, where z of t is the transmitted carrier, n of t is band-limited noise, and k is a constant that accounts for the attenuation of the modulated carrier between the transmitter and the receiver. And then it goes on to list equations. These equations show that all the components are affected by noise. Noise is a random process, so it can be described only in terms of statistical parameters. If the noise is zero, then the received and transmitted complex envelopes are linearly related. 5.1.2 The synchronization problem. The derivation of equation 5-6 assumed that the receiver had prior knowledge of the transmitter carrier's center frequency and phase angle. In practice, this information is not always known. The reference carrier at the receiver may have a phase angle error, or E of t, with respect to the incoming carrier. Instead of obtaining equation 5-7, the following equation results. Z base R of t exponent bracket negative j omega base 0 t plus j error of t bracket equals bracket k times the v of t plus n of t, or the time constant because it's capital N, bracket exponent bracket j e of t bracket. And then it says the noise can be simply replaced by another random process with a complex envelope. And then it lists the equation. And then it goes on to list a few more equations. And then these equations show that the magnitude function is altered by a constant and that the phase function is distorted by E of t, or the phase error. The received quadrature functions are a mixture of the original quadrature functions. This clearly shows the need to reduce the error. Section 5.1.3 Types of physical demodulators. Demodulators can be classified as coherent or incoherent. Coherent demodulators require external reference in order to demodulate the signal. This kind of demodulator must know the original carrier phase and frequency at the moment it arrives at the receiver. The incoherent demodulator does not need any reference because it determines only those parameters that can be measured in absolute terms. like frequency and amplitude. The two basic coherent demodulators are the homodyne detector and the phase detector. The homodyne detector consists of 4-quadrant multiplier followed by a low-pass filter. The block diagram shown in figure 5.2. Let E of t be the phase angle error between the reference carrier and the modulated carrier frequency. If there are no overlapping of spectral components between two terms in the preceding equation, the second term can be filtered out with an appropriate low-pass filter. And then it goes on to list a few equations in terms of the quadrature components. The phase detector is a phase comparator. Its function is to compare the phase angle of the incoming carrier with an external reference. Its output is proportional to the difference between the two angles. Due to the trigonometric function definitions, the phase comparator cannot distinguish between two phase angles that differ by integer multiples of where P bracket period denotes the operation of extracting the principal value of the argument. Equation 5-25 imposes a particular problem because it seriously limits the dynamic range of P of t. If E of t equals the phase, a constant, and the input is like the waveform shown in figure 5.3, the output will show phase discontinuities. This means that the original phase angle will be mutilated. If the phase angle error is due to a frequency difference between the reference and the carrier, the level where discontinuities occur will change periodically with time. It should be mentioned that the phase discontinuities will result in an increase of spectral occupancy of P base R of t. If noise is present, the output of the phase detector is found by substituting equation 5-10 into equation 5-25. There are two basic incoherent detectors. These are the envelope detector and the frequency discriminator. The ideal envelope detector recovers the magnitude of the received complex envelope. The ideal frequency discriminator recovers the instantaneous frequency of the complex modulated carrier. The output of an ideal envelope detector is R base E of t equals Ka base R of t. Therefore, it is unaffected by the phase angle. When noise is present, the output is identical to the equation 5-9. If noise is small compared to Ka of t most of the time, equation 5-9 can be approximated. The incoherent detectors have a threshold level below which the demodulated signal is severely mutilated by the noise, and above which the noise has little effect on the signal. Section 5.1.4 Coherent Universal Demodulators. The structures for the block diagrams of the coherent universal demodulators are a consequence of the structures for the universal modulators. There are only two feasible universal demodulation systems. These are the AM-PM demodulator and the quadrature demodulator. There is no PM-PM demodulator analogous to the PM-PM modulator because it involves three parameters. This will be discussed later. The AM-PM demodulator is shown in figure 5.4. It consists of an envelope detector, a phase detector, a baseband postprocessor, and an oscillator. A feedback path is provided from the baseband postprocessor to the oscillator to account for the possibility of reducing the phase angle error on the basis of the information available to the baseband postprocessor. The complex variables and functions are replaced by their real components, just like in Chapter 4. The second system is the quadrature demodulator. It consists of two homodyne detectors, an oscillator, a phase shifter, and a baseband post-processor. This is shown in Figure 5.5. Again, there is a feedback path from the baseband post-processor to the oscillator as stated in the previous paragraph. A system based on two phase detectors is not possible, although it is a modulator arrangement. The reason is that the transmitter knows the magnitude of the phase modulated carrier components and knows what complex envelope has to be generated. As equation 4-86 indicates, the transmitter knows L, phase 1, and phase 2. The receiver can take only two phase measurements. In other words, the triangle shown in Figure 4.2 of E cannot be constructed with knowledge of only of its angles and nothing about the length of one of the sides. There are other structures that can serve as universal demodulators. One of them is based on an extension of a system proposed by Zayedin, spelled Zayezdnyy, to demodulate. It is based on the generation of an analytic signal from the real modulated carrier using a Hilbert transformer. From the analytic signal, the amplitude and phase can be obtained. If equation 2-1 represents a narrowband modulated carrier, the Hilbert transform is, and it lists the equations. Another structure that will demodulate various types of modulated carriers is the phase-locked loop. The phase-locked loop has been analyzed in detail in various communications theory textbooks. It will demodulate most double-sided modulated carriers where a carrier term is present. If no carrier term is present, then additional modifications are necessary, and the system is more complicated and cannot be considered as a universal demodulator. Section 5.1.5 Incoherent Demodulators. It has been shown in Section 5.1.3 that the complex envelope must be recovered coherently or the components are distorted. It is possible to obtain approximations to the complex envelope components without a phase reference if the relative phase angle is not used directly. The incoherent AM/PM demodulator is shown in Figure 5.6. This system uses an envelope detector to recover A of t and a balanced frequency discriminator to recover the instantaneous frequency of the complex envelope. The system will be discussed in details later. Section 5.1.6 Criteria for comparison and evaluation of demodulators. The criteria to compare the different systems are the bandwidths required by the signals coming out of the detectors, their dynamic ranges, their noise behavior, and the effect of synchronization on the recovered message. The bandwidths and the dynamic ranges of the complex envelope components were already studied in Chapter 4. The reader should refer to Section 4.2 for information on the A of t and the P of t functions, and to Section 4.3 for the I of t and the Q of t functions. Since the noise problem is very complicated in itself, the analysis will be limited to qualitative aspects rather than to analytical work, because the main interest of this chapter is to study the system's feasibility and not their optimization. The same applies to the synchronization problem. Section 5.2 The AM/PM demodulator. The inputs to the baseband post-processor number 1 and R base E of t and R base P of t. The necessary equations for these signals are those obtained for the envelope detector and the phase detector. First, consider the noiseless reception with the zero phase angle error. There are only 4 different cases to study. Receivers that demodulate AM, DS3-LM, PM, and FM can demodulate CSSB-AM, SSB-LM, CSSB-PM, and CSSB-FM, respectively. For the AM and the CSSB-AM case, substitute the expressions for A of T listed in the Table 4-1 in Equation 5-29 with the noise set to 0. Consider the case where perfect synchronization is not possible. From the equations, it is seen that only the received phase function, P base R of t, is affected by the phase error. This means that if x of t can be recovered from R base E of t alone, there is no need to worry about E of t or the error. This is true for AM, CSSB-AM, CSSB-PM, and CSSB-FM. The CSSB-PM and CSSB-FM messages can be recovered as follows. In the CSSB-PM case, equation 5-17 yields R base E of t equals Kc times exponential bracket negative D base P of x of t in bracket. This is similar to a system proposed by Kane to demodulate SSB carriers incoherently. The disadvantage of this approach is that the message is obtained from the amplitude modulation instead from the phase modulation. Therefore, the advantages of angle modulation in the presence of noise are not being utilized. Now it only remains to find out if DSB-LM, SSB-LM, PM, and FM can be demodulated in the presence of a phase error. Consider the DSB-LM case. In this case, the absolute value of the message is linearly related to the magnitude function, and the phase function only determines the sign of the message. So the phase function assumes only 2 values. All that is necessary is to change the sign of x of base E of t whenever a phase jump occurs. This has a flaw. The output of the phase detector is also limited to the range negative pi to pi, so that the phase jump may be a result of P base R of t exceeding that range due to the error rather than due to the change in P of t. The estimated message x base E of t following this procedure is, and then they list the equation. This means that the original message is modulated. If the error is a constant, equation 5-55 predicts an undistorted output because the only phase jumps occurring are due to the carrier phase. If an error is the result of a frequency error, equation predicts sudden sign changes whenever P base R of t exceeds integer multiples of plus or minus 2 pi, while equations predicts a shift of all frequency components of x of t. Which one is worst cannot be predicted without further study. It should be noted that if the output of the phase R base P of t is used as the argument of a trigonometric function, it is not necessary to worry about principal value limitations. If R base P of t is used directly, like in FM and PM cases, the principal value limitation is of concern because it appears as distortion. From the practical point of view, the phase discontinuities are important no matter how R base P of t is used. These discontinuous points causes R base P of t to have a wider bandwidth than P base R of t. If the phase detector output stage frequency response is not wide enough, distortion will result even if R base P of t is used as the argument of trigonometric functions. The PM and FM phase functions are affected by the phase discontinuities discussed in the preceding paragraph because P base R of t is supposed to be a linear function of the message. If E of t is small, the principal value range is not exceeded often, and equations 4-9 and 4-5-50 can be rewritten. If E of t is a constant, the estimate of the PM message differs from the actual message by a scale factor and unknown constant. This constant can be eliminated if the output is obtained by DC decoupling in the baseband postprocessor. When E of t is a constant, x base E of t and x of t differ by a scale factor. If E of t is due to a frequency error, the PM demodulated message is distorted, but the FM message can be recovered by DC decoupling. This is true assuming that P base R of t does not exceed plus or minus pi. When noise is present, the inputs to the baseband postprocessor are obtained by substituting equations. For the small noise case, these equations simplify. This is the objective to the optimum receivers, and it is beyond the scope of this dissertation. It is mentioned to point out the possibility of optimizing the baseband postprocessor. In overall terms, the limiting case is the SSB-LM phase function because it requires the widest bandwidth. The functions A of t and P of t were analyzed in section 4.2. The dynamic range limitations are the same except that K base A and E base B. The maximum input to the balanced modulator has to be replaced by the maximum output of the envelope detector. Since this output may depend on the strength of the carrier, it is reasonable to assume that the RF gain of the front end of the receiver can be adjusted to avoid overloading the baseband postprocessor. Therefore, the actual dynamic range constraints are those imposed by the phase function. Section 5.3, the quadrature demodulator. The quadrature demodulator is easily analyzed for the noiseless case if perfect synchronization exists between the transmitter and the receiver. Let R base HI of t and R base HQ of t be the outputs of the two homodyne detectors. In section 3.2.1 and 3.2.2, it was shown that I of t components of the AEM, DSB-LM, and SSB-LM cases were linearly related to the message. Therefore, the output of the homodyne detector with the cosine reference is R base H of I of t equals I base R of t divided by 2 equals kx of t divided by 2. For DSB-LM and SSB-LM cases, and R base HI of t equals kc divided by 2 bracket 1 plus mx of t bracket for AM. It is easily shown that the estimate of the message is x base E of t equals R base HI of t for SSB-LM and DSB-LM cases. When synchronization between receiver and transmitter is not perfect, the outputs of the homodyne detectors are obtained from the equation 5.5-23 by observing that one detector uses sine and the other cosine. These equations show crosstalk between I of t and Q of t that will disappear only if E of t is an integer multiple of plus or minus 2 pi. Since R base E of t can be obtained from equation 5-67 and R base P of t can be obtained from equation 5-66, those modulated carriers can be demodulated incoherently from R base E of t can still be demodulated incoherently from R base HI of t and R base HQ of t. Although at first glance both systems seem to behave identically, there is a very important difference. The homodyne detector output does not exhibit an effect similar to the phase discontinuities observed in the phase detector. The only thing that comes closer to it is the clipping of the tops of R base HI of t and R base HQ of t when the detectors are overloaded. This can be solved by reducing the gain of the front end of the receiver. Only if R base P of t is computed, there is possibility of phase discontinuities. These discontinuities will occur inside the baseband postprocessor and not outside like in the AM-PM demodulator. Remember that P base R of t is computed only for the PM, FM, CSSB-PM, and CSSB-FM cases, so the only problems are the dynamic range restrictions on D base P and D base F. The troublesome phase functions were those for DSB-LM and SSB-LM that do not have to be computed here. It would be desirable to extend the dynamic range of the FM frequency deviation constant in order to detect wideband FM. Remember that in the quadrature modulator that was not a problem because the I of t and Q of t functions impose no restrictions on D of F. At the receiver, the problem is that it cannot distinguish between the angle y and the angle y plus or minus 2 pi because the receiver cannot remember the previous phase angle. If memory is added to the subsystem that computes R base P of t from R base HI of t and R base HQ of t, it is possible to eliminate the phase wrapping by making a correction to the phase whenever a large phase jump is detected. A system like this requires time delay. The correction has to be done after the phase jump is detected and not at the instant it occurs because the jumps cannot be predicted. The situation like this may be best realized with digital circuits because the delays can be accounted for easily. When noise is present, the outputs of the homodyne detectors are R base HI of t equals KI of t divided by 2 plus NI of t divided by 2, and R base HQ of t equals KQ of t divided by 2 plus NQ of t divided by 2, assuming perfect synchronization. Since Ni of t and NQ of t appear separately, it may be possible to reduce the effect of noise with special techniques at the baseband postprocessor. Section 5.4, the AM-FM demodulator. This section explores the possibility of using the AM-FM demodulator to recover the message from the carriers being considered throughout this dissertation. The system is an incoherent demodulator and the block diagram was presented in figure 5.7. The outputs of the demodulators of R base E of t and R base F of t given by equations 5-28 and 5-31 respectively. In a noiseless case, the AM, CSSB-AM, FM, and CSSB-FM presents no problem since these modulation laws can be demodulated from the envelope or from the instantaneous frequency. The cases that must be considered are DSB-LM, SSB-LM, PM, and CSSB-PM. Remember that the phase functions of DSB-LM is used to change the sign of X of t absolute, so it has only two values. The output of the balanced frequency discriminator is the derivative of the phase angle. Consequently, an impulse should appear at the output of the discriminator wherever there is a sign change. The baseband postprocessor number 3 detects the presence of the impulse and reverses the previous sign. This requires some memory to remember the previous sign. Since differentiation tends to emphasize the highest frequency components, it is reasonable to expect an increase in bandwidth of R base f of t over that required for R base p of t. This is critical for DSB-LM and SSB-LM cases whose phase functions are very wideband signals. The incoherent demodulation of SSB-LM has been studied by Volker and Hansen. Volker is spelled Boelcker. Hansen is spelled Hanson. Their solution is to add a small unmodulated carrier, C, to the SSB-LM carrier at the transmitter so that C plus x of t is less than 0. This restricts the phase angle to 0 greater than p of t greater than pi. The SSB-LM can be demodulated by envelope detection and a baseband postprocessor. Note that this requires modifications at the transmitter so it falls outside of what has been defined as universal demodulation. Incoherent demodulation of SSB-LM might be a possibility. Observe that when SSB-LM is at the input of the discriminator, the output is, and then they list the equations. To demodulate PM, observe that the message can be recovered from the instantaneous frequency by integration. This discussion shows that it is possible to demodulate most types of modulated carriers with an incoherent AM/FM demodulator, provided that some conditions are met. Practical considerations and comparison of demodulators. The demodulator configurations that have been suited in this chapter have been assumed to operate under idealized or controlled circumstances. The discussion has been centered on the qualitative aspects of the demodulator systems rather than in strict mathematical analysis. This section considers several aspects that have been ignored in the previous 3 sections. It is well known that most detector circuits involve a low-pass filter at the output. This filter is necessary to limit the noise only to the frequency band where there is a modulating signal. In sections 4.2.1 and 4.3.1, it was shown that the bandwidth of the complex envelope components changed with the modulation law and the modulation parameters. If the low-pass filter bandwidth is kept as wide as the largest bandwidth that is expected, the noise performance will be poorer for those modulated carriers whose components require a narrower bandwidth. A solution is to incorporate the output low-pass filter of the detector as part of the baseband postprocessor. The best results will be obtained when the filter passband is made as narrow as the signal component can tolerate. The improved baseband postprocessor is shown in Figure 5.9. Another important consideration is the effect of synchronization. In some cases, the phase information is important and it is desirable to synchronize the oscillator with the transmitter carrier. If a carrier term is sent by the receiver, synchronization can be achieved by filtering that carrier component, amplifying it, and using it as the reference. This may require a modification at the transmitter and may be equivalent to a change in the modulation law. The other alternative is to set a known reference signal so that the baseband postprocessor can adjust the local oscillator frequency and phase until the received signal is the same as the reference signal. This reference signal can be sent for a short time at the beginning of a transmission. In voice communication, the listener can adjust the reference oscillator frequency and phase until the received message is satisfactory. Finally, it is well known that the envelope detector has a noise threshold level. If the noise power exceeds that level, the recovered message is severely mutilated. This seems to suggest that the envelope detector should be replaced by a homodyne detector which has no threshold effect. This is not very restrictive to the designer because the phase reference is already necessary for the phase detector. The output of the homodyne detector is R base H of I of T, but R base E of T can be recovered from R base E of T equals R base HI of T divided by cosine bracket R base P of T. This equation is equivalent to an envelope detector. Noise threshold level can be expected to exist. This threshold can be lower than the level of the original envelope detector if some noise is removed from R base HI of T and R base P of T before calculating R base E of T with equation 5-76. The subsystem discussed here can be described with the block diagram shown in figure 5.10. The block shown inside the dotted line represents the baseband postprocessor. The quadrature demodulator was the best of the demodulating systems under considerations because it did not have the problem of wideband phase components that the AM-PM demodulator exhibited. The phase detector also suffered from phase discontinuities whenever the phase angle goes from the second to the fourth quadrant. This is very important since it results in wideband signals, and the phase detector output bandwidth must be wide enough to allow R base P of T to jump from one value to another with a very short transition time. Although the quadrature demodulator seems to require the phase reference at all times, it has been shown that it can demodulate AM, CSSB-AM, CSSB-PM, and CSSB-FM incoherently because the baseband postprocessor can calculate the R base E of T function using R base HI of T and R base HQ of T with equation 5-66. The incoherent AM-FM demodulator has the disadvantage of not being able to demodulate those cases where the phase function has non-zero mean value. Since the output of the frequency discriminator is equivalent to the derivative of the phase function, R base F of T was expected to have a wider bandwidth than the original phase function. Section 5.6 Summary. This chapter considered three different structures to demodulate various types of modulated carriers. Two of these, the AM-PM demodulator and the quadrature demodulator, are coherent in the sense that they require prior knowledge of the received carrier phase angle and frequency. The third system, the AM-FM demodulator, is an incoherent demodulator because the carrier phase is not necessary. This demodulator cannot demodulate any arbitrary modulated carrier because it requires certain conditions for the phase angle. The quadrature demodulator was found to be superior in performance when compared with AM-PM and AM-FM demodulators because it can recover almost any type of modulated carrier and does not present a troublesome phase detector. This chapter did not consider the details of optimizing the reception in the presence of noise. This is an optimum reception problem and is beyond the scope of this dissertation. Chapter 6 Conclusions. This dissertation studied the problem of obtaining transmitter and receiver structures capable of modulating and demodulating carriers following a variety of modulation laws. The general structure consisted of two modulators and a baseband preprocessor and the transmitter, and two demodulators and a baseband postprocessor at the receiver. The baseband preprocessor changed the message signal into two real-valued signals that were the complex envelope components. These signals were used to modulate the carrier. At the receiver, a pair of demodulators recovered the complex envelope components and the baseband postprocessor estimated the message. The types of modulated carriers under consideration were amplitude modulation, or AM, double sideband linear modulation, or DSB-LM, single sideband linear modulation, or SSB-LM, phase modulation, PM, frequency modulation, FM, compatible single sideband amplitude modulation, CSSB-AM. compatible single sideband phase modulation, CSSB-PM, and compatible single sideband frequency modulation, CSSB-FM. Chapter 3 studied some properties of the complex envelope components, namely the magnitude and phase functions, the conjugate functions. New results were found for the autocorrelation function of the complex envelope components for most types of modulated carriers under consideration, with the case of a zero mean Gaussian random process signal. Also found were the second moment bandwidths for those signal components whose autocorrelation functions were available. Chapter 4 analyzed the transmitter problem. Various modulator structures were considered and were shown to be equivalent to two basic structures. These structures were named AM-PM modulator and the quadrature modulator, respectively. The PM-PM modulator, a combination of two-phase modulators, was shown to be similar to the AM-PM modulator. Important results were the bandwidths that must be allowed for different complex envelope component signals and the parameter dynamic range limitations imposed by physical and mathematical constraints. The quadrature modulator was found to be the most versatile of all the systems under consideration because it offered the widest parameter dynamic range and the quadrature component signals did not require a lot of bandwidth. This modulator had the disadvantage of requiring more signal baseband processing steps than either the AM-PM or PM-PM modulators for some modulation laws. The AM-PM and the PM-PM modulators' weak points were the DSB-LM and the SSB-LM phase functions that require a lot of bandwidth compared to the other cases. The discussion in Chapter 4 also pointed out that the defining bandwidth in terms of distortion is better than defining it in terms of the second moment bandwidth. Examples were presented where the second moment bandwidth was too small for satisfactory results. In most cases, that could be corrected by adding a constant or using a scale factor. This constant was dependent on the type of modulation, on the complex envelope component, and in some cases on the message itself. The receiver problem was discussed in Chapter 5 from a qualitative point of view. Only two systems seemed to be practical. These were the AM-PM demodulator and the quadrature demodulator. The quadrature demodulator was superior to the AM-PM demodulator because it did not require wide bandwidths as the AM-PM did for the DSB-LM and the SSB-LM phase functions. The phase detector output of the AM-PM demodulator was limited to the principal value range. Consequently, if the received phase function exceeds plus or minus pi, the output of the detector will exhibit phase jumps that make the received phase function discontinuous. This makes the phase function occupy more bandwidth than necessary. These phase discontinuities get worse in the presence of noise or if the receiver and transmitter are not synchronized. In conclusion, the concept of universal modulation and universal demodulation has been shown to be a practical possibility. And this concludes the reading of Modulation and Demodulation of RF Signals by Baseband Processing, Cruz-Emeric, Jorge Antonio.